Hello. So in this slide, we talk about the relationship between frequency, energy, and the wavelength. So you can see that right here in this picture, I have drawn a sinusoidal waveform, and let's say it is an electromagnetic wave. So you see on the y-axis, I have an amplitude of that signal or electromagnetic signal, and it is a sine wave right here. And I start from this peak to this peak, and this period, I call it as a lambda. So lambda is nothing but your wavelength, and the frequency is denoted by f. Okay, so remember lambda and f. And now, if I start from this point, when the waveform crosses the zero on the x-axis is the distance. And from this point to this point, again, I have this period, I am calling it as a lambda. So lambda is a period which is called as wavelength, okay, on the x-axis. So how much is the distance it travels? So there is a relationship between frequency, energy, and wavelength. So you see that when we talk about a electromagnetic signal with a short wavelength, so we can see that it has a very high frequency. So the number of repetition right over here are maximum. But if we go on from short wavelength to the longer wavelength, so you see this, the time period between this point to this point again. So, and here, between this point to this point here, right here. So you see they are shorter wavelength, about 410 nanometer. So it means short wavelength means high frequency and high energy. Long wavelength means low frequency and low energy. All right. So there is a relationship between that. Frequency equals to c over lambda. Lambda is wavelength. What is c? C is the speed of light. It means the speed at which the electromagnetic waves travels from one point to another point is called as the speed. And that speed is equivalent to the speed of light, which is 3 into 10 to the power 8 meter per second. So if I say that I have a signal, electromagnetic signal of 1 megahertz, and I want to know in a certain medium, we'll see that in a moment, I want to determine the lambda of this particular signal, find out the lambda. So what I'll do is that there is another, if I know that f equal to c over lambda, it means lambda equals to c over f. Just I'm manipulating this equation right here. So lambda would be c over f. So lambda will be 3 into 10 to the power 8 meter per second, which is the speed of light right over here, divided by 1 megahertz. So 1 megahertz is like 1 into 10 to the power 6 hertz, right? So I can say that, okay, it is about 3 into 10 to the power 2 approximately or exactly. So it is like 300 meter, okay? So that's how I can determine the speed, I can determine the lambda or wavelength of this particular signal. Now, next term is the energy indicated by E, which is given as it is equal to H time F. What is H? H is the Planck's constant, and its value is 6.626066 into 10 to the minus 34 meter square kg per second. So if you want to determine the energy of a signal of any electromagnetic wave, use this formula, H times F. If you don't know the if you want to use another equation, you can always plug in the value of f in this equation right here. So it becomes E equals to H times C divided by lambda. H multiplied by C divided by 1. C divided by lambda is nothing but your frequency. All right, so this is how you can calculate and determine the relation between frequency, energy, and wavelength. Just to summarize, small wavelength means high frequency and high energy. Long wavelength means low frequency and low energy. So here we can see that the speed of an electromagnetic wave, as we have seen that, we can read this sentence here, and we see that the electromagnetic wave travels at the speed of light, c, in vacuum. So we are assuming that in a media where there is no air, the electromagnetic wave is traveling in the medium called as vacuum. It will travel at the speed of light, c, and the speed of light is approximately 3 into 10 to the power 8 meter per second. So that is how we have seen that.